use CMQ, you use 1000. If you use DMQ, you use 1 only. That's 1.0. So with these cheats, you will be able to get any solubility question without wasting time. Hello, welcome once again to Somebody's The Easy World Science channel, the Easy World of Science. Today, I will help you get the easy cheats on how to deal with solubility calculations. So today, I will handle solubility, the definition, on the way you have to get your, if you want to know the solubility of an unknown solute that is soluble in water, the procedures and the approaches. And don't forget to subscribe and also book for your own private classes for your schools and for your kids or you yourself, because I'm here to help you learn chemistry. This is the easy world of science. We make science easy for you. Don't forget to subscribe, of course, and share my videos. First, what is solubility by definition? Solubility generally means actually the quantity of a given solute that is required to saturate a given quantity of a solvent at a particular temperature. So while defining solubility, you must consider the amount of solute that will provide a saturated solution when dissolved in a given amount or in a given volume of a solvent. But for the sake of calculation, you can define solubility in a standard way as that solubility is the amount, that solubility of any substance is the amount of that substance that is required to saturate 1000 cm cube or 1 dm cube of a given solvent at a particular temperature. Remember that temperature is necessary while defining solubility, because change in temperature changes solubility. So solubility depends on the temperature at which the solute is being dissolved in the solvent. And solubility of a given solute also varies from one solvent to another. Some solutes dissolve in water, some don't. Some solutes dissolve in ethanol, some don't dissolve in ethanol. So while discussing solubility, we have to consider solutes and solvents. So for standard definition, the standard volume for solvents should be 1000 cm cube, which is also equal to 1 dm cube. So before then, if you want to assess the solubility of an unknown sample, as you can see here, the procedure involved, let's take a look at this. If you want to determine the solubility of copper 2 Tetra Oxosophage 6 in water, what you need is just a measuring cylinder. Here you first add a known volume of water. Here let's assume we will use, okay, this is 30 cm cube. So this known volume of water, 30 cm cube of water. What you do is you keep dissolving the solute until it becomes saturated. How will you know it is saturated? When the solute is no more getting into the solution, such that the rate at which the solute gets into the solution is at equilibrium with the rate at which the solute is being displaced from the solution. So you add, and then instead, let's remove. Remember, you have your paper where you have to record that the volume of water initially is 30 cm cube. So as you can see, this is not yet saturated, it's taking more of it. So we dissolve again to give us a saturated solution. And it's also necessary you take note of the temperature of the solvent. Here is my thermometer. So at least it's showing us that this is at a normal room temperature reading, nearly 20, which is about 27 degrees. Then you put it into the solution. So it is still 27 because I don't heat the water. So now I am considering the solubility. Okay, I don't heat the water. Now I'm considering the solubility of copper 2 tetroxosulfate 6 in water at 27 degrees Celsius. Okay, you can see closely that it's no more dissolving. We have undissolved solute. Shows that what I have now is a saturated solution of copper 2 tetra oxosulfate 6. So when you produce a saturated solution, to make the result, make sure the whole particle is dissolving. So when you get a saturated solution, the next thing to do is to filter the solution. That's to remove the undissolved solute. Let me check again if it has taken it off. No, there are still undissolved solids.
So you are filtering to remove the undissolved solids. Now, after the filtration, what you need to do now is, as you can see, the filtrate is dropping. You get the filtrate, then evaporate to dryness. Then take the mass. Take note of the mass of the solid sample you recovered back. And remember, our original volume is 30 cm3. So when you weigh it, you can easily calculate the solubility of this sample. Let's assume that after this filtration and the evaporation to dryness, I'll get something like, let's say, 15 grams of CuSO4. Remember that 15 grams of CuSO4 now saturated 30 cm3 of the water I added originally. So to know the solubility of this, I'll now ask myself, if 30 cm3 were able to take 15 grams, whatever 1000 cm3 takes gives me the solubility of this salt. So in that aspect, you cross multiply such that 30x is equal to 1000 times 15. So we have that's 15,000. 30x is equal to 15,000, such that x is equal to 15,000 divided by 30. So we have here 15 divided by 3, 500 grams per dm3. So this should be the solubility of, let's assume this is what we get after the experiment. Therefore, this should be the solubility of copper 2 tetra oxosulfate 6. At what temperature? Remember, 27 degrees Celsius. So this is the procedure on how to get the solubility of an unknown sample. Okay. Next, let us face the calculations. First, there are basic things you need to know here, that 1000 cm3 is equal to 1 dm3, which is equal to 1 liter, which is also equal to 1000 milliliter. So all these things, this is the standard volume, and as far as water is concerned, 1000 cm3 of distilled water is equal to 1000 grams, meaning 1000 cm3 of water is the same thing as 1000 grams, because the density of water is 1 gram per cm3, meaning 1 cm3 of water weighs 1 gram. Therefore, 1000 cm3 of distilled water will also weigh 1000 grams. So in the calculations in solubility, we are taking note at the first step. 1000 cm3 is equal to 1 dm3, which is equal to 1 liter, which is also equal to 1 milliliter. Which is also equal to 1000 milliliter. Now, students always find it difficult. The simple cheat is here. There are 2 units for measuring solubility. Solubility, you can use gram per dm3 as way of expressing solubility, or you use mole per dm3. There is what we call molar also. Molar means the number of moles of a solute in 1 kilogram of a given solvent. So when we say molar, maybe when I say 0.1 molar copper 2 tetra 6, meaning 0.1 is in 1 mole per dm3. And some authorities say that this is also known as molarity. So unit for expressing solubility is also unit for expressing concentrations. Now, for concentrations, for solubilities in gram per dm3, we go with the formula. Just use the sheet. Solubility in gram per dm3, simple, is equal to 1000 times mass given, or gram given, all over volume given in cm3. Simple. Or you say that gram per dm3 is equal to 1 times gram given, that's mass given. Gram given and mass given is the same. Divide by volume given in dm3. Divide by volume in dm3. The difference here is that
if you are the volume given to you in the question, if it is in CMQ, you use 1000. The volume given to you, if it is in DMQ, you use 1. Remember initially I told you that 1 DMQ means 1000 CMQ. Then solubility in mole per DMQ is also this: 1000 times mole given times mole given all over volume in CMQ. That's cubic centimeter. Or you can say that mole per DMQ is equal to, just like the other, 1 times mole given all over volume in DMQ. Then, if you are given in mass to find in mole per DMQ, you can also say that mole per DMQ is equal to 1000 times mass given all over molar mass divided by, that's, you should divide all these things by the volume, in CMQ. Remember, if you use CMQ, you use 1000. If you use DMQ, you use 1 only, that's 1.0. So with these cheats, you'll be able to get any solubility question without wasting time. So, when looking at the formula I gave there, I hope cameraman, you're getting it. So the formula shows that we have concentration in gram per DMQ, concentration in mole per DMQ. If you are finding or if you are calculating for gram per DMQ, it simply means you need to take 1000 times the mass given to you, any mass given to you, not the molar mass given to you in the question, all over volume given to you in the question in CMQ. Or you say gram per DMQ is equal to 1 times mass given or gram given divide by volume given in DMQ. So these are the ways to get it in a simple way. So quickly we'll rush into many examples. So the first example we'll take here, you see there on the screen clearly, but I read it out. The solubility in mole per DMQ of 20 grams copper 2 Tetra Oxosophage 6 dissolved in 100 grams of water at 180 degrees Celsius. Remember, you are not going to use the temperature. The temperature is just to tell you that temperature have a great effect on the solubility of solutes, especially solid solutes in liquids. If you increase the temperature, solubility increases. If you decrease the temperature, solubility decreases. So in calculation, in answering this question, they say solubility in mole per DMQ. So first step, you see any solubility question, first of all, note the mass given in the question. Given mass. From the question, it says the solubility in mole per DMQ of 20 grams. So the given mass is 20 grams of CuSO4. Next thing is volume given. The volume given to us there is 100 grams of water. 100 grams of water. Remember, I told you that 1 gram of water is equal to 1 cm. So this is a volume. This 100 grams of water means 100 cm cube of water. Therefore, go back to this thing here. You use this sheet which says what? The mole per DMQ is equal to 1000 times given mass or mass given divided by volume given in cm cube. This gram is equal to cm cube. 1 gram equal to 1 cm cube as far as water is concerned. So all over volume given. Simple. What do we have? 1000 times mass given 20 all over volume given 100. Cancel. So that what we have here now is 5 and here is 1. So we are actually with 1000 divided by 5, which will give us
200.
200, right? Okay, yeah. So it's going to give us 200 gram per dm cube. So what do you do? Remember what? Use this one now. To get the mole per dm cube, you can solve straight by saying 1000 times mass given, which is 20, all over molar mass. Molar mass of what? Copper 2 Tetra Oxosophage 6. So let me look at the question well. the molar mass of copper 2 tetraoxide 6, in brackets, you can see there on the screen that copper is 64 plus 32 plus 16 times 4, which is 64. So we have 64 plus 64, giving us 128, right? 128 plus 32.
160.
Okay, we have exactly 160 gram per mole. So the molar mass of copper 2 tetraoxide 6 is 160. So you have 1000 times 20 over 160 divided by volume given, which is 100. So you go straight and find this. So we have 1 over 8, that is 1000 times 1 over 8, all divided by 100. So 1000 by 1 over 8 is 125, then divide by 100. So that should be 1.25 gram. Sorry, 1.25 mole per dm cube. That's our final answer. Right, remember the cheat I used? 1000 times mass given all over molar mass, and this 160 means molar mass divided by volume given. Okay? We see another example. You see the question there on the screen. I'll read it out again. I've cleaned. Okay, example 2 you see there on the screen is if 12.2 grams of lead-2 triazole-nitrate-5 were dissolved in 21 grams of distilled water at 20 degrees Celsius, calculate the solubility of the solute in mole per dm cube. Calculate the solubility of the solute in mole per dm cube. So they gave us the molar mass straight to help us. So in this case, I told you, solution to the question you see there on the screen. First of all, you write out the mass given. Mass given. The mass that was given, if you watch there on the screen, is 12.2 grams of what? Lead-2 trioxynitrate 5. Then the next is what? Volume given. The volume given from the question is 21 grams. 21 grams of distilled water. Remember that 21 grams of distilled water is the same thing as 21 cm cube of distilled water. Now, next thing you do is, what are you asked to calculate? Are we calculating solubility in mole per dm cube? We go back and check. Or are we calculating in gram? Or are we calculating in gram per dm cube? From our question, they asked us to find the mole per dm cube. Then, there was a mass given, not mole. So we go back to our formula which says that mole per dm cube is equal to 1000 times mass given all over molar mass divided by volume given. So remember, we are discussing lead-2 trioxynitrate-5. It should be 331. To get it clearly, lead is equal to 207, nitrogen is 14, oxygen remains 16. So when you do this calculation, you find out that the molar mass of lead-2 trioxynitrate-5 is 331. And as a student, you should endeavor to memorize some molar masses of some common compounds. Like lead nitrate is 331. This lead nitrate is important to memorize. It's 331 because you might make mistake trying to calculate the exact thing. Then copper 2 tetraoxide 6 is 160. And we just saw now. Sodium chloride is 58.5. Sodium hydroxide is 40. That's the molar mass. So these things are necessary. You memorize common molar masses of some common compounds. Now, substituting the values from here, we have that 1000 times, what's the mass given from the question? 12.2 divided by molar mass. Molar mass is 331. Divide now all by the volume given is 21. Remember, if this volume is in dm cube, I'll use 1 here instead of 1000. That's the cheat. So here we go. First, you just get the answer of 12.2 divided by 331, which will give you 0.036. Here we have now 1000 times 0.037 on the approximate divided by 21 is our final answer. So multiplying stress, we have now what is the numerator there is 36.86 divided now by 21.
so that our answer is 1.75 mole per dm cube. This is our final answer. So this cheat, whether you understand it or not, just know the mass given, the volume given, and know whether the volume is in dm cube or cm cube.
Now carefully watch this question. It says if 117.0 gram of sodium chloride was dissolved in 1.0 dm cube of distilled water at 25 degrees Celsius, determine the solubility in mole per dm cube of sodium chloride at that temperature. Carefully watch this question. The volume was given in dm cube, unlike other examples you have been seeing where volume is in cm cube. Therefore, you use this formula which says 1 times mass given over molar mass times volume in dm cube, and the volume was 1.0 dm cube. Therefore, at the end, you just have that mass given all over molar mass gives you the solubility.
We take another example, question there on the screen, and I read, when 50 cm cube, that's our volume given, 50 cm cube of a saturated solution of sugar of molar mass 342 gram at 40 degrees Celsius was evaporated to dryness, 34.2 grams of dry solid was obtained. The solubility of sugar at 40 degrees is, when I look at the options were given to me in mole per dm cube. So, using our normal cheat,
I never believed in dreaming.
First step, you say mass given. Given mass is, be careful, 34.2 grams. The other mass is molar mass, please. This one is mass given. Then volume given to us from the question is 50 cm cube. So remember, this is the cm cube, so we are working with 1000. When in dm cube, we work with 1. Then the next, are we looking for the solubility in mole per dm cube or gram per dm cube? We are looking for solubility in mole per dm cube. And in this case, from the cheat we have 1000, solubility in mole per dm cube equal to 1000 times given mass all over molar mass divided by given volume. So this is your given volume, given mass, and this is your molar mass. And the question said that the molar mass of the compound is equal to 342 from, okay, yes, of course, 342 grams. So what do? Our answer will now be 1000 times the given mass is 34.2 divided by this, which is the molar mass, 342. Of course, we'll be getting something like 0.1 or so, then divided by volume. Given volume, the volume given was 50 and is in cm cube. That's why we are working with 1000. Okay, we get our answer first. For case of clarity, we have 34.2 divided by 342. You have your 0.1. So the answer here, this one is 0.1. So what we have? We now have that 1000 times 0.1 all divided by 50 is our answer. So when you have this, automatically this is going to give you 200 divided by 50, which will give you 2 moles per dm cube. Our final answer. So you don't need to crack your brain to see that this cheat is working. Now, another aspect that students find difficult is when they give you a higher and a lower temperature, asking you for the mass precipitated and also for the amount of extra solute that is taken. Don't worry about that. I will now give you the cheat for that one. So we will see calculations involving solubilities at different temperatures. Sometimes the common one is to tell you if 100 grams or 250 or 150 grams of a saturated solution of this is cooled from 80 to 30. Sometimes, very rare, they will ask you what if the temperature is raised from 30 to 80. What should be the solubility? We will see the way out. This one will require your clear understanding of it before you can solve well. So here I will just go with an example. This is going to be a too strange question, but you see there on the screen. If 50 grams of lead 2095 saturated 100 grams of water at 30 degrees and 75 grams of the same salt, that's lead 2095, saturated 100 grams of water at 80 degrees Celsius if the temperature of 200 grams of saturated solution of lead 2095 is raised from 30 to 80 degrees Celsius. Calculate the extra mass of lead 2095 that will dissolve in the saturated solution at 80 degrees Celsius. This type of question is somehow lengthy, but it is easy. Your work is take note of the mass of solutions at the different temperatures mentioned. So your first step is the temperatures mentioned. The first temperature mentioned is 30 degrees Celsius from the question. If I'm right, then you take a look at mass of solution at 30 degrees Celsius. Remember that mass of solution is equal to mass of solvent plus mass of solute. Mass of solvent plus mass of solute. Because solution is made up of solute dissolved in a solvent. Now, from the question, you write out the mass of solute at 30 degrees. Watch down the screen. The mass of solute at 30 degrees is 50 plus the mass of solvent is 100 grams. So, we are now dealing with 150 grams of saturated solution. This is the mass at 30. Then, second temperature mentioned. The second temperature mentioned is 80 degrees Celsius. When you look at the screen, you find out that the mass of solution at this temperature is equal to the mass of solute in question is 75. Then the mass of solvent remained 100 grams. So remember, 100 grams of water means 100 cm cube of water. So total mass is 175 grams at 80. Then it shows now that raising 30 to, when you raise 30 to 80 degrees Celsius, it means that there will be extra dissolution. How do you get that? You now have that this is raising, not minus. Your job is just to use the higher one to minus the lower one. So what we have, 175 minus 150. So the extra mass consumed is automatically 25 grams. So what does it mean? That 150, take the mass you got at the first temperature, simple, that's your control. 150 grams of saturated solution, when raised to 80, took extra 25. That's a known fact, you put it down. Don't use 175 because that's the new solution. The original was 150, but when the temperature was increased from 30 to 80, it accommodated extra 25 grams, which now made the mass become 175. So you keep this fact, fact 1. Then you go now to the question. You go down to the question, and they said, they just gave you a saturated solution again, which is, okay, 200 grams. Now, since 150 grams gave me 25, simple. If 200 grams of saturated solution is raised from 30 to 80, it will automatically give me X, as far as it's the same salt. You cross multiply. So what do we have? We have that 150X is equal to 25 times 200. So using our calculator, we have that 25 times 200 is 5,000. So 150X is equal to 5,000, such that X is equal to 5,000 divided by 150. 33.33 grams of lead nitrate will be dissolved. That's the extra mass it will take. So that's the way out. Let me take the explanation again. After the whole grammar you saw there on the screen, just take a look at the mass of solution at the first temperature, then take a look at the mass of solution at the second temperature, then minus the mass of solution at the second temperature from the mass of solution at the first temperature. After doing that, you use the mass of saturated solution at the first temperature, equate it to your answer. That's the answer you got here. Then go and bring the volume.
that was given, the volume of saturated solution that was given, and put X here, you have your answer. So let's take maybe, this is a case where the temperature is raised from 30 to 80. But what if the question is cooled from 80 to 30? Which means I will use my first temperature as this place, changing the whole thing. Your work is just whether it is telling you when the temperature is cooled from 80 to 30 or raised from 30 to 80, 20 to 60, 60 to 20, whatever temperature. You're not going to use those figures. Your main interest is to know the mass of solution at the first temperature mentioned. Then another thing is to know the mass of solution at the second temperature mentioned. Then minus these two masses. Use the higher one and minus from the lower one. Then use the first mass of solution at the first temperature, equate it to your answer, then bring whatever they ask you and then answer. So try yourself in this question you are seeing there on the screen and check what you can have if you have really gotten the answer. Then sometimes another aspect is solubility products. Students often try to fear solubility products. By definition, solubility product is actually the product of the concentrations of ions in a saturated solution. So it is just trying to control for you to know when precipitation will take place in a solution. That's when a precipitation will occur in a solution. Like as you can see here, we filtered in the beginning. If the concentration of ions here exceeds the solubility product of copper 2 oxosophage in water, what happens here is that there will be precipitates. Precipitates will occur. But just know that it's a work of the solubility product is just a figure that helps you know when precipitates will occur. And remember, it's a product of the concentrations of the ion. And how would you know it? So the solubility product, let's assume we have AX, BY, that is at equilibrium with each solution, which gives us AX plus YB. The solubility product, assuming now that this is undissolved, of course, aqueous, this is undissolved. The solubility product is just equal to taking it like an equilibrium constant, because the undissolved and dissolved is at equilibrium, like I taught you when I did saturated solution. As you can, if you watch here clearly, there is still undissolved. What happens here is that as the undissolved is going in, the one dissolved is being displaced out. So the rate at which the copper 2 oxosophage goes into the solution is the rate at which it comes out. So this is a saturated solution because of undissolved. Then, which means the solubility of undissolved is going to be taken as 1. In other words, remember your equilibrium constant. This is just our solubility product, AP. Solubility product is now B raised to the power Y. Why this is molar concentrations of A and B. Divide by AX and BY raised to the power 1. Now, taking the solubility of this as 1, it shows that the solubility product, this is taken as 1, of course, because it's undissolved. Remember, this is solid. So when this is taken as 1, it shows that our Kp is now equal to raised to the power the coefficients. Multiply this raised power to coefficients all over 1, which is the same thing as this. So this is the solubility product of a given solute that is in equilibrium with this solution. Let's assume they gave us that the solubility product is maybe 20, let's use it as 20 grams per mole or 20 grams per GMQ. If you find out that on multiplication of what was given to you is above 20, it means that precipitate will occur. When it is below 20, it means that it is not yet saturated. So with solubility product, you can know when the solution is saturated, when it's unsaturated, and when it is actually supersaturated, and when there is a tendency of precipitate to occur. God bless you. Thanks for watching. Her Majesty Easy World Science Channel remains good for you. Share my videos and don't forget to ask your questions, and also book for your private classes, live streams, anywhere you are all over the world. I will reach you. Ask your questions down there in the comment box. Remember to follow the community guidelines. Don't forget to press the button, like, and share my videos. God bless you.
It's a song we learned in Zimbabwe. You are Alpha